Alright guys, so here is the explanation for the extra practice for the complex ions and stability slide. The question here, what is the concentration of copper 2+ in a solution that was originally 0.015 molar copper nitrate and 0.1 molar NH3? The other information that's given is the Kf value for copper NH3 complex. So this is going to be my complex ion. And if I'm giving you this Kf, the first thing you should do, and hopefully you guys are getting sick of hearing me say this, is write out the chemical equation that corresponds to that Kf. So since this is a Kf, that's a formation. So here I'm drawing out the chemical equation that will correspond to the formation of the complex ion. And of course, this has copper and NH3 in it because that's what, my complex ion is made up of. Here we're going to see that we have nitrate, right? And I think we might get a little confused by that, but that goes back to what we've been saying all quarter long. If I give you a Kf for copper NH3, that's going to be what you draw out your equilibrium for. Doesn't matter that there's nitrate in here, right? That's just going to be, in this case, a spectator ion. And we really know that simply because this problem, deals with this formation of copper NH3. So we don't really care about this nitrate. And you've got to be able to differentiate and know when we can do that and when we can't do that. So here the Kf equals 4.8 times 10 to the 12th. Right away I'm noticing that this is huge. Right, so that is a huge Kf value. And as I talked about in class a little bit today, this is really going to be, for the initial part of this problem, just a stoichiometry limiting reactant type problem. So, pulling in some numbers here, we might, consider this to be the initial conditions, 0.015 molar for copper 2+, and again, that's from this copper nitrate, 0.015 molar copper nitrate. Well, that's my source of copper 2+, so I can put that in there. And then for NH3, 0.100 molar. Now, again, like I said earlier, rather than doing this sort of as an ice table, we're going to do this as a limiting reactant stoichiometry table. So I'm going to start with some amount, I'm going to end with some other amount, limiting reactant, so here 0.015, that's going to be the limiting reactant. I'm going to end up with 0 copper 2+. All of this copper 2+ will turn into this copper complex, so I'll have 0.015 molar copper NH3 complex once this reaction has sort of gone to completion. Again, I'm treating this as a reaction that goes to completion first because this Kf is so huge. Now, for my concentration of NH3, then we need to use this multiple ratio, right? It's a 1:4 ratio, 1:1 ratio here. That's why those two values are the same. But here, this is going to be a 1:4 ratio. So at the end of this reaction, I'm going to end up with 0.04 molar. So if I take 0.015, I multiply it by 4. That's how much of this NH3 will be consumed. Subtract that from 0.1, I get 0.04 molar. Okay, so now at this point, these are the values, and in my mind, these are the values that I'm going to use for my Kd expression. I like flipping this around. You don't necessarily have to, but I think it just makes a little bit more sense in my mind. So now I'm going to do from the point of view of Kd. So let's move this up. Copper NH3 for 2+, dissociating, right? Dissociating. I'm going to get copper 2+ plus 4 NH3. And this is my general form of the Kd, right? Dissociation of my complex ion. And my Kd value is just going to be 1 over my Kf, or 2.08 times 10 to the minus 13th. So very, very small. So again, my x value is probably going to be very, very small. Now I'm going to do my ice table. So my initial here, 0.015 molar, 0, and 0.04 molar. So now I'm going to do minus x plus 4x, right? Don't forget that. In this case, it doesn't really matter since it's going to be negligible anyhow, but just a good practice. And then I'm basically going to solve for x, right? So 2.08 times 10 to the minus 13th equals x times 0.04 plus 4x to the 4th power. Don't forget that. Really easy thing to forget there. Something that I will forget all the time. 0.15 minus x. My minus x and plus 4x terms will be negligible because my Kd is so small. That makes solving for x a lot easier, and I get 1.2 times 10 to the minus 9th molar. Now this x value, right, that is equal to my copper 2 plus concentration, which is exactly what I'm looking for in this problem. I could then, relate that to other things as we've looked at further, but for this question, that's my final answer. Okay, now just a real quick plug for going back through this problem and really understanding and figuring out what's going on here. Why are we saying that this is a stoichiometry limiting reactant problem? What does this KF value tell us? How are we getting this KD? Where does that come from? How are these equilibrium reactions related to one another? So having a good sense of all of this and when you might do this, is really the point of these videos. So I don't want you just to copy everything down. I want you to go back over it, be able to explain this problem to someone else. All right.